for Camille to show that you have listened well. The floor is yours.
Thank you, Tina. Yes, I'm just hoping that everything was smoothly in the room and online, and please let us know if there is any technical issue with the sound camera. I'm very pleased to present you my work. I've been working on some years already. So the work is entitled Weight of Circular Buildings, Enhancing the Material and Environmental Impact Assessment of Reuse Strategies in Buildings. And I wonder if you notice when you enter this building, if the slide can come in. Yes. Did you notice when you enter this building, you receive some building information in the form of this little signage panel that is now more and more common in public buildings and in Belgium, in the EU, and abroad as well. That shows you how much energy is consumed by the building and if there is any kind of renewable energy production in this building. And it's great because we're trying to reduce the energy consumption of building. We're trying to phase out of fossil fuels. But this doesn't show the whole picture, right? There is one crucial element that is not visible there on this picture, and it's the material aspect. Because buildings are responsible for a large consumption of material and a large part of the waste we are generating. Actually, half the materials we are extracting from the earth are used in the building sector. And the building sector will then produce approximately a third of all the waste that we are generating. So as architects, builders, or as anyone who is making decisions about buildings, if you are renovating your house, for example, you have a role to play in trying to reduce this material flow and reduce this waste. And I'm not only talking about the waste that is generating during construction of buildings. As you know, there is always a container on the construction site where the waste material, some waste material end up. But there's also some waste and some material consumption during the operation of buildings. That means all the maintenance, all the repairs and upgrades we are doing to our buildings to make them fit to our evolving requirements. And obviously, there's a lot of waste that is generated when we are demolishing and renovating our buildings. So what can we do about it? Well, to reduce material consumption and to reduce waste, there is a concept called reuse that you can use, and actually two possible reuse strategies. The first one is to design with reclaimed materials. And that it's not to be confounded with recycling, because reusing reclaimed materials means taking materials from existing buildings, cutting them, reclaiming them, transporting them to a new location, or sometimes somewhere else in the same building, to use them instead of using new materials. And we have an example here where the architect have decided to sew brick panels from a building that was going to be demolished and transport them to install them in a new building, in this case in Copenhagen. And the other reuse strategy that I will talk about in this presentation, it's called design for disassembly and adaptability. And as we know, our needs are evolving, our regulations are evolving, what we expect from a building is evolving. So why do we want to build something static that will not evolve easily? Well, that's a problem that can be addressed with design for disassembly and adaptability. And that means, for example, using building elements that can be easily removed from building with reversible connections, or then that could mean having visible ventilation equipment, lighting equipment in case of necessary upgrades or repairs. And in this case, the Circular Retrofit Lab, well, it's an experimental building here on the campus of the VUB. It's testing out and trying to go a bit extreme in this design for disassembly and adaptability concepts. And you see, for example, raised floor that grant easy access to the water pipes. But the FDA doesn't have to look experimental or unconventional. It can also have a similar appearance as a normal house. For example, in this case, where the facade click system was used in this building to build a facade, but not with mortar, fixed brick, that make them very difficult to reclaim and reuse, but using a plastic insert within the brick that they can read it more easily. So yeah, I could keep on and talk about reviews and design for the assembly for hours, but what I want you to remember for the rest of the presentation is that with the FDA approach, it's important to have easy access to the building parts that are most often replaced or changed in a building, and use reversible connections so that we can safely and without waste change or adapt to buildings. So that is great because those strategies are becoming more and more popular, more and more put forward in the practice, in architectural practice, in education, in policy. So we see that more and more, but we have to remember that it's not a goal in itself. The goal is to reduce waste and to have better material management, right? And it's not enough to know that, okay, we'll use reversible connections, so we'll have a circular building, or we'll reclaim some elements, so we'll have less waste and less material consumption. No, it's a bit more nuanced than that. We want to know how much and where and what would be the impact of implementing those strategies in the building. So we want to have a way to measure and estimate the future material flows and the future environmental impacts of buildings that integrate reuse strategies. How can we do that today? Well, we are lucky because there is a method that is called life cycle assessment, LCA, that allows assessor to have an environmental impact of a building or product. And not only today during the construction, but with a life cycle perspective. So now I'm just going to give you a very quick basic overview of LCA, and then I will raise some points of what I see are limitations in LCA that could be addressed with alternative approaches, and then we'll dig a bit more in detail into two of these limitations. So LCA uses material and energy consumption data to estimate the environmental impact of products. And to illustrate that, I will take a very simple and recurring example in LCA. Let's take an espresso machine, for example. Well, with a life cycle assessment perspective, we will look at the production of the machine, its use, and its end of life or disposal. And for each stage, we will look if, okay, what kind of materials, energy, waste, and emission are taken in and generated by these processes. So we'll have some steel and some plastic that are used to produce the machine, and that will create maybe some waste. And when we'll use the machine, we'll use coffee grounds, we'll water, energy that will make coffee, hopefully, and then some coffee waste, steam. And then at the end, we will try to disassemble and treat the different parts of the machine. Right. This machine, hopefully, everything goes well, we build it to last 15 years. And logically, the LCA will also encompass 15 years of the life cycle of the machine. Now, if we take an example in the built environment, let's say a simple brick that is made for 200 years or more. But because we use it in a building that will generally last 50 years or a large maintenance or a major renovation of 50 years, then we do an LCA over 50 years only. So there's a first already discrepancy between the lifespan of this product and the scope of the life cycle assessment. And then if we are inspired by circular economy and reuse, we'll say, okay, maybe we will try to reuse this brick after the first use in a building. But well, in conventional LCA, there are some criteria and conditions that allow us to consider this future reuse. And in this case, one of the conditions is we'll consider reuse possible only if there is a market or demand for this product today established. Well, that's also a bit problematic if we're trying to evaluate what could be the potential benefits of more unconventional, more rare and niche reuse practices. And then there's another aspect that what if we use this brick conventionally with mortar, or what if we try to assemble them in a bit of a smarter way with this plastic insert that I was showing a bit earlier? Well, in conventional LCA, there's not a clear difference between the two ways of using this brick. because of, we'll see in some minutes, because of the way the conventional LCA method is designed. So these are the kind of little issues we collected. So I collected throughout the year of the research, and that led me to ask myself, okay, how can we assess reuse strategies in buildings in a more nuanced way than with conventional LCA? And I addressed this research question in 3 types of research methods. I first critically reviewed the current standards for life cycle assessments and past studies of life cycle assessment. I also tested out these methods in 4 case studies. 2 case studies that are more putting the accent on reclaimed building materials, and 2 that are more putting a focus on design for disassembly and adaptability. And then I also, of course, consulted experts in construction field, in academia, in circular economy and LCA. And of course, this was a bit of an explorative approach based on reviewing critically what the current use of the standards, what kind of information they give us, what kind of information they omit, and how we could do things differently to, in the end, inform the design decisions and guide the application of reuse strategies in buildings. And that led me to develop 2 sets of contributions. A first contribution, which is a bit putting the accent on the methodological choices in LCA, so alternative definitions of the functional units of the LCA, the system boundary, and scenarios. And the second contribution that is then putting more the accent on the modeling of the use and reuse of building parts in the inventory phase of the LCA. And there is one term here it's important to clarify before we go ahead and dig into each of these aspects, is the system boundary, because it's quite important when you talk about reuse in LCA. And if I come back to my example of the espresso machine, well, the system boundary is this limit, artificial limit we set around or the life cycle of products and the different materials and processes that we include in our assessment. Because, of course, in an LCA, you could go upstream and upstream and upstream, and from the coffee ground, look at the soil in which the plant has grew up, and then come back and back and back. So we could go on and come back to dinosaur time if we would not put a limit into, okay, this is what matters, and this is what we want to include in the assessment, and this is what we leave out because it's less relevant to the system that we want to assess. Yes, so let's dig in the first set of contribution. And for that one, so I thought it's a little bit more of an exploratory approach. And I used 3 case studies. That's how I will structure these parts. I will not present them all now, but I will explain to them one by one. The first case study was and could be useful for a second life. And decided to create an urban greenhouse with this leftover woods or wood wastes, and also collecting glass panes from old windows that have been replaced from buildings. And then he said, okay, why should we only design the building, the greenhouse for one use? Let's make it modular and use reversible connections. So maybe we could transport the people and transport and relocate to a different place if needed. Okay, that's great, but with a conventional LCA, typically we would set our boundary on this second use of the wood and the glass pane, and the third use, the second reuse would be declared in outside our system boundary. because of the way conventional LCA is currently set up, this second reuse is not, we cannot claim benefits from using this material a third time. So how can we actually account for using fields in closed loop, so in a circular way? And then I wondered, okay, maybe use a method that is a bit closed, which is called yeah. Okay. Let's okay. Try. Yes. Yeah. So an hemisphere of this greenhouse. Yeah. With the production phase of the greenhouse, the use and the F of life, as we saw before. So that is a conventional one use of the greenhouse. But what if we would have flows coming back into the production stage thanks to this demountable and adaptable design? So that could be a way of throwing in the assessments the benefits of having the DFT approach to the design. A second case study was the roof truss, which I explored in collaboration with the PhD researcher Jan Gutting at EPFL. And there we wondered, okay, if we had a building and we had options with either demolish the building or totally build and construct it. I hope it's okay for those. You want me to switch to a different microphone? Okay, yes. Now I'm more in the voice setup than PhD. Okay, good. Yeah, so we could demolish or we could deconstruct, right? And if we construct, maybe we could sandblast the parts and reassemble them into a roof truss or a structure to have a roof of a building. And we would like to compare this with the more conventional approach of demolishing the building, transporting the elements to a recycling plant, and then recycling the steel into steel members for this, let's call it new recycled truss. So how to compare those two systems? It's a little bit problematic in the conventional LC approach because typically we would put the limit between previous building and this building at this stage. But we want to have a fair comparison between the two systems, the reused one and the recycled one. So we decided to adapt the system boundary so that yeah, we can more easily compare or have more insight to the impact of both approaches. And then in a third case study, that is coming back to the brick that I was presenting earlier, the one that have a plastic insert and that can be disassembled and reused up to 5 times. Well, with a conventional approach, system boundary would typically include the first use and put the first reuse of the brick in this module called module D, and would not include any subsequent use of the bricks. Well, that's not helping us because we want to understand what is the impact of reusing this material 3 times, 4 times, or what is the effects that different transport distances have on the benefits of reuse or the different material losses. So instead of that, we could actually expand the system boundary and include the different uses of this reusable building part into the system that we are evaluating. In doing that, we need to adapt what we call the functional units in the LCA. So this declaration of the functional performance of the product. And well, instead of phrasing this functional unit as one use of the material, of the product into one building, maybe typically 25 years, the replacement rate of the finished layer of a facade, we could have a bit of a longer use of this product so that these different uses are included in our system. So in conclusion, in this first contribution, I have tried out with different definitions of the system boundary, of the functional units, and of the use scenarios. And that revealed that with those adapted definitions, we can get some different kind of insights on the impacts and the comparison between reuse approach and a conventional approach, and also different aspects or different scenarios in reuse strategy. But of course, that doesn't answer all the questions, that raise actually more questions. And if you're interested in the detail and the actual results of this life cycle assessment, I encourage you to read the book. But here I will just mention two possible future exploration that I see. One is to look at the way we phrase the functional units and have possibly a dynamic approach to the way we frame it. And that could be, for example, inspired by the work of Charlotte Camille. In her master thesis, she assessed the life cycle costing, so the costs on the life cycle of a building, but comparing conventional building to expandable building. So houses that grew with the size of a family when you have more children or you need extra care or help at home. And another possible exploration is the aspect of the material rebound effects of circular strategies. So in the brick case study, we compared this demountable facade that is going to be used in different buildings and then eventually disposed of. We compared that to a conventional facade that is used then the same number of times. But one can wonder if it's actually realistic to compare 3 times the construction and demolition of a facade to this reusable facade. Maybe because our product is demountable, we would like to demount it or change it more often than the conventional product. So there might be some kind of rebound effect because it's demountable, so we might need to or want to reuse it more. Yes, so that was the first contribution of this PhD research. Now we'll move on to the third contribution, which is the building approach considering dependencies between building parts. And for this approach, I will first present this contribution. I will present you the conventional approach to model replacement in buildings. I'll show you what's the proposed alternative approach and what it looks like when applied on the case study. The conventional approach to evaluating replacements and future changes in building is quite simplistic in the conventional LCA standards. If you remember, these two aspects were critical in very important in design for disassembly and adaptability, having easy access to building parts and using detachable connections. But what we see in the LCA standards is the number of replacement of a building parts depends on 2 parameters: the lifespan of the building and the lifespan of the building parts. So imagine we have a building that will last 50 years and a pipe in the building to have 10 years lifespan. Well, it will be replaced 5 times. It's 4 times, so use 5 times 10 years. But this method or this equation does not take into account what is the accessibility of the pipe. Is it demountable? Is it modular? This is simply not in this equation. So possibly some waste or some incidental wastage of material is not captured by this equation. And also, if an architect would want to design for this assembly, this is also not captured by this approach. And that is problematic when we want to use LCA to support better informed design decisions. we would like to know how much waste is generated, how many parts can be reused, and how many new parts needs to be installed in the building to replace those lost parts. So if an architect would design a building with the different parts of a building, what would be the effect of using reversible connection, or what would be the effect of non-reversible connections? So that's one approach, and another option is, if we had a base design, how is this base design comparing to an alternative design where the type of the building or any kind of technical equipment in the building, instead of being placed inside the wall, is placed outside, and thus more accessible to make the necessary changes and upgrades. And then we could have a third approach or third design that is more modular, and where the panel of the wall is split in two, so that if we need to access this pipe, we can only remove half the wall and make the necessary changes. So as I said, with the simple equation that we have today in the standards, all these different designs, so the spatial designs and the 3 types of connection, all have the same life cycle assessment fact, because those different parameters are not part of the equation. And that's not what we want. What we want is a more nuanced comparison of this design, different design alternatives. So this is what we want. How do we get there? The question becomes how to model material flows due to changes in building in a more nuanced way than conventional LCA. And that brings me to the proposed approach. This proposed approach was developed in first, researcher François Denis and we developed the conceptual basis for the concept of this alternative approach to model replacement, and published it in 2019. And then we received funding from the UB to develop a concept, so funding to program the concept of METSUP into a BIM plugin. And then we tested and published the case study results in a journal article in 2022. And of course, we don't start from scratch. We are inspired by previous research that have developed life cycle assessments and life cycle costing approach for elements. But these approaches were designed for layered elements, like walls, like ceiling components or flooring components. So where you have a layer by layer approach of assessing the mountability of the component. And that is a good start, but not what we need for having a 3-dimensional assessment of the demountability of a building. And what's been inspiring as well is research in product design and product disassembly modeling, like we have here in the 90s, and as well as researchers at research who have conceptually adapted this product design approach to the building. So the approach that we're proposing is to start from the model of building with different parts, different components, and I will here use an even more simple case just to show you step by step how this method is working. So let's take a portico model, just 2 columns, a beam, a cross-bracing element, and 2 wall panels. This model is then translated into a network graph where the different nodes of the graph are the building parts, and the arrows between different nodes are the structural connections between the building parts. First, if you try to disassemble something, it's not disassemble it. You also know accessibility dependence between building parts. So here, the cross-bracing elements between the 2 walls can be accessed by either disassembling the first wall and then access it, or we can disassemble the second wall and access it. We have an or between the two graphs, two options. Those two network graphs can be merged into combined graph, which then show you all the structural and accessibility dependencies between building components. And so highlight that to reach that, we can start from there, remove connection between wall 1, column 2, and wall 1, column 1. Or the alternative approach is to start from wall 2 and then disassemble the connection between wall 2 and column 1 and 2. Of course, I'm showing you a simple or simplified step-by-step method. In reality, this method is a bit complicated. We have behind each node of graph metadata that carry information about not only the mass of building parts, but also the cost, the impact. And so we could optimize disassembly according to different parameters like time, cost, or weight. Just to summarize, we start from a building model including parts, connection between parts, and how they are spatially composed. We translate that into a network graph of structural and accessibility constraints, and that gives us the disassembly sequences. So the sequence of parts and connection that needs to be disassembled and removed to access the target part, which in this example is the cross bracing. From there, we can then characterize the connections, whether we have reversible or non-reversible connection, or a mix of connection that will preserve one of the two building materials, either the attached part or the hosting part. Thanks to this information, we can then sort out in the preserved flow, in the damaged flow, or reclaimed flow. And that then gives us how much waste, how much material can be used, and how much new materials need to be introduced in the building to replace the damaged equipment. What does that look like when we apply this on our case study, which is the simple pavilion that I was showing earlier? So if you have those three connection designs, so non-reversible, partially reversible, and only reversible connection, these are the connection graph we would see. So the non-reversible connection is completely red. It's a bit of an extreme, unrealistic example where detaching any part of this pavilion will lead to either of the two components being damaged and non-reusable. And then we could have a mix of reversible and non-reversible connection. And the other extreme of everything is completely reversible, we can reuse any part of the building. And if we run these assembly sequences over the service life of the building, we can start to see, okay, at year, for example, 25, we would need to replace our pipe here inside the wall. But thankfully, because everything is reversible, we can just remove the wall panel, change the part that is needs to be replaced, then back without creating waste, without consuming new building materials. But at year 30, then the wall panels need to be replaced. So that means that we will have another bump in the graph. And again, at year 50, we will have to replace the pipe equipment. With this graph, we can start to see the differences on material flows over the lifespan of the building. And we can compare that to our second design. So the partially fixed connection, where then we see one graph. And again, this non-reversible design where every time something needs to be replaced, then the whole pavilion needs to be replaced, which is realistic, but just to show you the range of material flow we can expect over the service life of the building in some extreme cases. That was for the different kind of reversibility of connections. Now, if we look, we can also look at the spatial designs, the base design, the accessible one, and modular one, and combine it with the other connection design to then have 9 design alternatives, which we can compare with those graphs, but also with a material flow or total life cycle assessment impact for the different connection. And there we see that even with fixed connections, so non-reversible connection, that leads to every time we need to make a changes, both components are damaged. Also, that even with fixed connection, with a base layered and accessible design in blue, we can actually manage to reduce the operational impacts of the building by half. So it's quite good. And of course, this is a simplistic case. A building like that cannot be built, but it shows you the range of information we can get from applying this kind of approach. And so in summary, this approach that is called disassembly network analysis, or DNA, can model material flows due to changes in building in a more nuanced way than conventional LCA, because we see the differences in for the different designs. And it's more a dynamic approach because we see the impact changing over the service life of the building. And secondly, it's also a bottom-up approach, a bottom-up modeling of material flows, and it means that we can link the impacts of the material flows with specific parts, specific connections of the building. So it's a little bit more nuanced. You can see, okay, if I would have to change one aspect of the building, then this part or this connection could be made reversible to save then some material on a life cycle approach. And yes, it's a first conceptual method, and it could be refined in different ways. And one way to refine it, I think, would be interesting to compare what would be the modeled material flows with material flows that we would measure empirically. And this is something that I have been actually starting doing with some experimental disassembly of wall setups. And secondly, it could be interesting to refine the way we define accessibility of parts. So currently in the method as it stands, the user has to provide this information into the model. But might be a way to have this information automatically using building information modeling. And this is actually something a master student started working on and developed a plugin to have automatic detection of the accessibility to building parts. Yes, in summary, my research started from critically reviewing what are the existing approach methods to assess environmental impact and material flows in buildings, so LCA and MFA, and developed a set of recommendations on findings. First one being that the current LCA standards can limit the assessment of reuse strategies on the whole life cycle perspective, as I was mentioning at the beginning of this presentation. But also that an expanded system boundary could aid in understanding the environmental impacts of relocation and reuses. Thirdly, that the impact of displacements are likely underestimated in current LCA calculations. And it could be interesting to consider the effects of DFDA in life cycle assessments, and that could be enhanced by applying this DNA method that was developed in the research. So concretely, for architects or anyone involved with life cycle assessment of building, it could be interesting to think of reusable products not as the use of the product in one place by one actor, but more like a consumer good, like the coffee machine. If I move it and I give it to someone else, the end of life of this coffee machine is not ending there. We can continue considering this machine as still having a use, proper service life, and test then this expanded system approach. Then it could also be interesting to assess various scenarios for the future reuse of building parts and identify what are the threshold values making it more or less interesting than the conventional use of or linear use of building products. And finally, it's also important to think of this incidental waste during future replacement. So not just only considering the service life of the building parts and the service life of the building, but also, okay, we have access and we need to remove some other building components before accessing these parts. And what are the dependency between these parts and surrounding building parts? So I hope that in the future, if this research keeps expanding, we'll get not only an energy performance of the building, but also a material performance of the building with hopefully not just the construction impact, but the whole service life of the building. Thank you.